Yeah, I can see the recording. So I hope you can see my screen or the shared presentation.
Yes, we can.
Okay, great. Thank you. So thank you so much first of all, for the invitation to be here and present my work, and also thank you for the introduction. So I don't need to do that. Just very briefly, I am Daniel Paluba, postdoctoral researcher from Prague, Czech Republic, and today I would like to share you more information about our work, where we are trying to estimate optical vegetation indices and biophysical parameters using SAR data through machine learning approaches for Central European forests. So forests are covering approximately 1/3 of Earth's land surface and also Europe's land surface, and they are one of the most important ecosystems of our planet. However, they are dynamically changing, and these changes are caused by various disturbances influenced by anthropogenic or natural factors. For example, the yearly deforestation rates increased or more than doubled in the last 20 years, while wildfires caused approximately 1/3 of all forest losses globally. Also, in Central Europe, we are encountering several problems, such as, for example, the bark beetle infestations, which spread uncontrollably in the last few years, while Czech Republic was referred usual or often as the epicenter of these calamities. Luckily, we are living in the era of big data in Earth observation and cloud computing technologies, which enables us to monitor our forest in almost near real time. So actually, Earth observation data and methods, especially multi-temporal approaches such as time series analysis, can help us and enable us to better and faster localize various changes and dynamics in forest ecosystems. In the recent years and decades, various Earth observation-based forest indicators have been developed, while most of them came from optical satellite imagery. They are well-founded, often used by decision makers, by researchers, and also in private sectors or by non-specialists in Earth observation. And this is done in various sectors, from forestry, agriculture to other ones. However, when we are dealing with optical-based satellite imagery, we need to deal with atmospheric effects such as clouds, fog, haze, or smoke, which make our measurements actually unusable for land monitoring or forest monitoring. So as a workaround solution, we could use synthetic aperture radar imagery, which signals can penetrate clouds. We can monitor the Earth's surface with SAR data during day and night. So in that case, they are offering insightful and complete time series. On the right-hand side, we can see a comparison from Šumava National Park from Czechia, where on the left-hand side we have a NDVI time series derived from Sentinel-2 data. After all the pre-processing and cloud masking, we could get approximately 70 cloud-free imagery for a 4-year period. On the other hand, when we use Sentinel-1 SAR data for the same area and for the same time range, we could get actually 10 times more Sentinel-1 imagery. So here we can see really the advantages of SAR data or monitoring the land using SAR data. So with that, we wanted to do the so-called SAR to optical translation to make actually SAR data more useful or readable for also non-experts in the SAR technology. And here in the first step, we needed to prepare an approach to join and align data from various modalities or from various sources, then to apply machine learning approaches to estimate standard vegetation indicators. With that, we aim to support the current essential climate variables and well-founded vegetation monitoring approaches in a much higher temporal resolution as it is done currently using optical vegetation indices, for example. So in the very first step, we needed to prepare our forest dataset, which was generated in the first step by a forest mask, which was a strict forest mask using an overlay of 4 different datasets, publicly available datasets, which are aimed for forestry or they are land cover datasets in Czechia. And then based on these forest masks, we generated our random points, which were further validated with time series of high resolution imagery from Google Earth Pro. And based on these, we selected our forest areas for further analysis. Then we created a spatially and temporally aligned multimodal time series dataset. So maybe you're asking, what is it? Actually, it contains pre-processed data from Sentinel-1 SAR mission, from multispectral mission Sentinel-2, also pre-processed data. We include also topographic information from digital elevation model from Copernicus, and also meteorological information from ERA5 land reanalysis dataset. Based on this approach, we also created a tool in Google Earth Engine to create multimodal and multi-temporal time series datasets anywhere on the globe. And this dataset or this tool is actually available on GitHub and can be used anywhere where you want. And here you can see a short demonstration how this tool can be used. So the users can actually select the time frames or the start and the end date for the analysis, select if the user wants to generate some random points or use his own features. So for example, own vector layers for time series generation. Then the user can select the pre-processing steps or parameters for Sentinel-2 and Sentinel-1 SAR data preprocessing. He can select the temporal difference between SAR and optical data, which is by default 12 hours here, and then just apply the settings and run the analysis. And then very quickly, the user can get the final time series prepared for export, and he can export actually as a CSV file. So you can get more details on the provided tool in our study, which was published actually last year. And in this study, you can find also more information about the identification of optimal Sentinel-1 SAR parametric parameters for forest monitoring in Czechia, where we did also some correlation analysis between optical vegetation indices and the SAR features and so on. After that, when we had all our time series prepared, we could move to the next step, the main goal of this work, to estimate vegetation indices and biophysical parameters, when we were trying to estimate normalized difference vegetation index, so NDVI, enhanced vegetation index, EVI, leaf area index, and FAPAR. Here, we were comparing two traditional machine learning approaches. One of them is random forest, then the second one is the extreme gradient boosting, which were also fine-tuned for the task. And we are comparing them with actually the so-called automatic machine learning approach, specifically to AutoScaler. Very briefly, what this automatic machine learning approach does, it does all the data preprocessing, the feature preprocessing, selecting the regressor, its hyperparameter tuning in an optimization loop, while it also using meta learning for warm start, and at the end it can build an ensemble model from the best performing models which was found. So actually, when it comes to the results, we can answer our question that or our question from the title of this presentation, that yes, we can estimate optical vegetation indices and biophysical parameters using SAR data with much higher temporal resolution compared to Sentinel-2 data, and this temporal resolution can be up to 240 measurements per year when we are using two Sentinel-1 satellites. When we added additional ancillary features, such as meteorological and topographic data, we can enhance the accuracy even more. And here, at this point, I would like to highlight the importance, or I would like to highlight why it is important to explain how our model is working and what it learns from input data. So on this figure, you can see the Sentinel-2 based NDVI, so the original NDVI values. Then there you can see two attempts. The blue one is the SAR-based NDVI trained on Heathly forest, and the second one is trained both on Heathly and these two forests. And when we take a look on the first attempt, which was or the modeling results based only on Heathly data, we can see that it actually achieved very high accuracies. It performed very well when it was estimating actually Heathly broadleaf or coniferous areas. but it failed totally in case of disturbed areas. But why it is happening? The reason is that when we take a look at the feature importance analysis, we can see that the most driving factors are the day of the year, so the temporal information and the forest type. So that means that in this case, the model learned the patterns from time actually. So it was pretending, or it was estimating also the disturbed area, that it was healthy area based on the just temporal information. We can see that also the importance of SAR features, which we really aimed for, are very low and almost negligible in this model. On the other hand, when we also include disturbed areas in our training, while disturbed areas were labeled as coniferous areas, we could make actually the importance of SAR features much higher, and they were really contributing to the modeling task. And here with this model, we can see that we could change, we can monitor the changes and also the disturbed forest, which was disturbed before this 2021. And with this approach, we were also able to increase the temporal accuracy of disturbance detection from 42 days using Sentinel-2 data to only 4 days using the SAR-based NDVI. Then, when we were comparing various machine learning approaches, we found out that the fine-tuned random forest and extreme gradient boosting achieved better results than the automatic machine learning approach, while these approaches were less intensive computationally and in case of time consumption or intensity. Also, the extreme gradient boosting was the most efficient algorithm we used, which was in some cases 70 times faster than the random forest. We did all this training and testing for Czechia for 1.8 thousand areas, but we also wanted to test our approaches and our models for a wider area, for an unseen area. So this is why we generated 4,000 other areas outside Czechia in Central Europe to test the transferability of our models. And regarding the results, we achieved very comparable results and high accuracies also. If you want to know more details about this study and these results and the methodology and so on, there is a study which was published actually this year in February in Big Earth Data Journal, and we are also providing the best performing machine learning models on Hugging Face and also the data and supporting codes for reproducing the results. But we didn't stop here. We also wanted to enhance our modeling even more with new enhancements actually, and this is why we added additional layers or features, and one of them are the lagged SAR features. So these are actually the average backscatters of 7, 14, and 28 days before the actual measurements. We also added the snow masking for Sentinel-2 data because we found out that there are some problematic areas during winter time in Central Europe. And we also expanded the temporal coverage for training and testing from 1 year to 5 years. And at the end, we found out that the extreme gradient boosting, which was the most efficient one, so this is why we used this one for further testings, had an improvement in R square up to 10%, for example, for NDVI. And we also found out that our resulting time series, the estimated time series, were less noisy, especially for disturbed areas. And we can see that it works really well for 1 year for 2021 and also for a much longer time series, for example, for a time series of 8 years. So to conclude it, in this study, we were able to bridge SAR and optical measurements to create more easily usable and readable results also for example, non-experts, which are used to use, for example, vegetation indices or biophysical parameters. And we could do that with an improved temporal resolution, which was nearly 200 measurements per year using just 2 satellites. But we are really looking forward to have data from Sentinel-1D. That means there will be 3 satellites or 3 SAR satellites, so even higher temporal resolution could be achieved. Also, when it comes to machine learning approaches, we found that the fine-tuned traditional machine learning approaches can outperform more sophisticated approaches such as automatic machine learning when the extreme gradient boosting showed as the most effective approach. And here I would like to again highlight that ensuring the explainability of our results is essential actually to make our machine learning or AI systems more transparent, more trustable, and they are also very good to validate our assumptions to really understand how our model works and what it learns from our input data. And currently, actually, we are using these approaches and also other approaches to detect various forest changes, detect forest phenology, and understand climate-biosphere interactions. And if you have any other ideas, I would be very happy to discuss it with you, how to use this approach. So with that, I would like to thank you for your attention. Also, thank you for the invitation for Panjo's cost action. And yeah, thank you.